the whiteboard.
Sì, si vede.
Okay, fine. So let's start a new topic. The last thing I said last time, okay, was that we're going to now look at there. Okay. Oh, it's recording. Okay, fine. Can you see the whiteboard? Yes. We're going to see two prototypes. Okay, prototypes. By prototype, I mean sometimes we call them toy models. Okay, models that are very, very small, so that they retain essentially the basic aspects. Okay, of what is going on in the sort of kinetic process of combustion. So we're still talking about chemical kinetics, we're talking about combustion, and now we want to essentially illustrate two prototypes, okay, of kinetic models. In fact, what I said is that these two prototypes, in fact, will happen, or these two modalities, okay, of combustion will happen at the same time, okay? So in particular, we said that one was the so-called chain branching, and very soon I'll explain what this means. But the word chain, in a way, must sort of remind you of the chain reaction, okay, kind of concept. And the other one is thermal explosion. Okay. So the chain branching is a toy model that we're going to analyze at constant temperature, in the sense that all of the reactions that we're going to be considering in the mechanism are going to be characterized by a constant rate. Okay, so a constant K, which does not vary with temperature, because temperature is kept constant. Okay. On the other hand, with a thermal explosion, we're going to be considering a very simple one-step reaction, where essentially the rate of reaction will retain the exponential dependence on temperature. Okay, so the two things, of course, will live together in an actual combustion reaction, because you have both the chain branching aspect, so an aspect where you have the production of a large number of intermediate species. We're going to see this today. But you also have that for each of those reactions, there is a dependence on an exponential dependence of the rate of reaction from temperature. Okay. Now, if we can separate these two aspects, we will try and understand them fully and more closely, okay, one by one, okay, individually, because they have different mechanisms, okay, whereby they can actually lead to explosion. I said explosion or thermal, or runaway are interchangeable terms, in the sense that what we're looking at is a very, very, very rapid release of heat and production, and generally speaking, oxidation of the fuel into products. Okay, so that's what we mean by explosion. Now, clearly, in the thermal explosion, you will have an exothermic reaction of some kind, so production of heat. In the chain branching, we're considering T equals constant, so you're just going to have a very fast reaction, meaning change from the reactant to the products, okay, by way of a large number of intermediate species. So let's look at this chain branching. let's say, system, or here I can also call it a toy model. Okay, it's going to be a very, very small toy in the sense that there is no molecule, actual molecule involved, so it's a symbolic formalism that we're going to be using. But on a large scale, this can be reproduced, okay, with any combustion of any fuel in oxygen, okay? Okay, so in chain branching, we will consider, in fact, three different kinds of species that we're going to be identifying with letters. So it's, again, a symbolic formalism. So R is the reactant. C is the starts for chain carrier. Chain. Sorry, this is okay. But we can also call it intermediate species, or even a radical species. Okay. And finally, P will be the product, the final product. Okay. So these are it's a minimum set, let's say the minimum really number of possible species that we can configure in this chain branching system. A chain branching system is a mechanism, okay? It's a chemical kinetic mechanism composed essentially of three steps. The first step will convert, okay, the reactant, which you can think of the either the fuel or the oxidizer or both, okay, which turns this reactant into a chain carrier, C. Okay, so in an intermediate species C. So you see that we're not transforming the reactant into the product directly. Okay, we're going through the production of this intermediate species, and this will have a reaction rate, which we can call it Ki. I stands for the initiation step. Okay. So it has a rate constant Ki, which we consider in this instance as being a number, or okay, a constant. So it produces one radical from the reactant. Now, usually we call branching, okay, steps that produce a net quantity, positive quantity of chain carriers or intermediate species. So you see here, for example, in this irreversible step, you have the production of one chain carrier C starting from zero. So you have a net production of one chain carrier. So this is also formally a branching step. Again, where branching means a net production of intermediate or chain carriers, okay? So we're starting to, so this could be, for example, the composition of, or the, of a fuel molecule, for example, okay, that breaks up into smaller molecules that are having some covalent bonds that are or free valence that are open to react. So that's why these intermediate species C, in fact, are representative of a large number of different kinds of radicals, okay, that usually have one or more electron free valent bonds that are again available to be shared within a covalent bond. So that's why they are extremely reactive molecules. Now, the second step is the actual chain branching step. What do we mean by that? Well, the intermediate species that we've just produced above will again react with the reactant, okay, in an irreversible manner, in this case, with a rate constant Kb, to produce, well, a first molecule of product, but also alpha molecules of the chain carrier itself, okay? So this alpha will be a parameter that we're going to use in this analysis. So this is a free parameter that's going to be very, very important, okay, in this analysis. So this is we call it a branching step. Okay, where in which alpha radicals, okay, or alpha chain carriers C are being formed for each chain carrier, okay? So for each chain carrier C, you're producing alpha. Now, clearly, if alpha is equal to 1, well, this reaction is really not a branching step, right? There is no net production of C. In fact, it's what we call a propagation step. So all it's doing, it's propagating C, okay? But it's not producing more molecules of C than it's actually depleted, okay? And the third and final step will be a termination step, which we can call, whose rate constant we can call Kt, which essentially terminates the intermediate species C to form the product, okay? So this could be, for example, well, this we call it termination. What this could be? It could be a recombination, for example, a reaction. Okay, or the oxidation, for example, of CO and CO2. Okay, this would be a termination step where CO is an intermediate and CO2 is a final product. So you see, we have essentially a very, very complex mechanism of hundreds and hundreds of reactions, in fact, can be summarized with 3 sort of prototypical reactions, okay? An initiation step, which is needed to insert intermediate species in the system. A branching step, which again is crucial to explain why a reaction can be very, very fast, okay? Because we're producing essentially alpha times radicals that we are actually, when we're depleting 1. So alpha could even be less than 1, in fact, okay? But then we'll see that for alpha equals 1 or less than 1, this mechanism will not be effective, okay, in really generating a very, very fast reaction. And then clearly these intermediates will have to disappear from the system through the termination step where the products are actually being formed. So again, it's a formalism, okay? We're not attempting to recreate an actual system, but clearly a kinetic system like the oxidation of methane or any fuel or even hydrogen and oxygen, okay, involves a certain number of intermediates. So think of for example, the oxidation of hydrogen and oxygen, okay? We can think of the reactants as being either hydrogen and oxygen. The products will be water, and the chain carriers will be all these sort of intermediates. So like OH, like atomic hydrogen, like atomic oxygen, H2O2, and so on, okay? HO2, these are all intermediates, combination of species that are rather reactive, okay? And that will essentially be intermediate between essentially the reactant, okay, and the final formation of products. Okay. So now let's see in more detail what's going on. So a chain branching reaction is a reaction for which, so I'm talking about this intermediate reaction here, the branching step, okay, is a reaction for which alpha is generally bigger than 1, larger than 1, so that you can have the production of more radicals that you put it than you have actually put in. Okay? We'd like to understand, first of all, irrespective of whether this is fast or slow, okay, the overall process. So we're not looking at the 3 steps here, we're just looking at this process here. Okay, we're going to be looking at y, okay, in a sort of mechanistic way, why this particular reaction, if alpha is bigger than 1, can actually induce a very, very fast process, a very, very fast explosion. Okay. You can also address these molecules C with a little dot to remind ourselves that this is a molecule that has a free electron. Okay, but really you can actually neglect that. Okay. So this would be the sort of the representative of the free valence. Okay. Now I'll give you an example. Okay, I'll give you an example so that we can understand why this sort of little machine here of sort of chain branching mechanism here. It's not even a mechanism. It's a little. I call it a little machine, a chemical machine that produces more intermediates than it's actually depleting. Why it can cause a very rapid explosion. So suppose that you have a vessel, okay, a volume, which can be, for example, 1 cubic centimeter, okay? So this is the volume of our little vessel here, okay? And suppose that we have a large number of the initial reactant molecules. So, for example, 10 to the 19 molecules per centimeter cubed of R. Okay? So initially, you have a system full of molecules of R, okay? In fact, 10 to the 19 molecules, because we have 1 cubic centimeter, okay? And suppose that we start out with just 1 molecule of intermediate species, of chain carrier C. Okay, so this is our sort of initial state. So there's just 1 little molecule of C, but mostly R, okay? 10 to the 19 molecules of R. And I will give you also a collision rate, okay? Which is the rate at which C and R, okay, can collide per unit time. So how many collisions you have per unit time. So I'm giving you reasonable numbers, okay? So 10 to the 19, well, suppose the Avogadro number is of the order of the Avogadro number, so it's 1 centimeter cubed. So at normal pressure, atmospheric pressure, at the constant atmospheric density, you more or less have 10 to the 19 molecules in 1 centimeter cubed. Now, collision rate, reasonable number. Well, it's obviously dependent on temperature, as we know, and on molar concentration. We've seen that. A collision rate of 10 to the 8 collisions per second, okay, is reasonable. Okay, so C and R will collide 10 to the 8 times every second. Okay, very good. So with these numbers, can we give a rough estimate of the reaction time. Okay, so I'll just write here. What's the reaction time? Well, what do we mean by complete reaction? Well, when all of the R molecules, okay, have been essentially depleted. So in order to complete the overall reaction, okay, and transform essentially all of the reactant molecules R into product, remember that we also have, we can write it here, but we have sort of a terminating step where C then becomes the product. Well, we need to have that all of the 10 to the 19 molecules of R will have to collide, okay, with molecules of C, okay? So suppose now that alpha is equal to 1. So what are we talking about? We're talking about a reaction where you have one intermediate reacting and colliding with R, forming a product, okay? And then one other intermediate, okay? So what do we do with this intermediate? Well, it will react with another molecule of R with the same process to produce another product plus another intermediate. So you have this disappears, this appears, okay? But then there is going to be another product, another process where this disappears, this appears. So you essentially at every time you have just one molecule of C progressively colliding, okay, with all the molecules of the reactant, okay? Do you think it's a very fast process? No, in fact, it's a very slow process, this one, because clearly it's a sort of a propagating step where you essentially always having one molecule of C, okay, which has to collide with all of the 10 to the 19 molecules of R. So in fact, you can estimate for alpha equals 1, you can estimate the time of reaction to be, well, how many collisions do you need? Again, you need 10 to the 19 collisions simply because you always have one molecule of C at every time, so it has to collide with all of the molecules of the reactant at every present in the system. So 10 to the 19 collisions is what we need. Okay, we have a collision rate, which is 10 to the 8 collisions per second. So you see this is a time because it's at the denominator you have 1 over time. And so it's 10 to the 11 seconds. Sorry, can you see it's 10 to the 11 here? You can still see what I'm writing, right?
Sì, sì.
What's 10 to the 11 seconds? Does anyone guess? Well, if you divide by 3,600, you have hours, you divide by 24, you divide by 365. Again, you have about, I don't know, something like 3 times 10 to the 4 years, okay? Given a collision rate which is completely realistic, okay? So it takes one molecule essentially of C, okay, this many years, okay, to actually collide with all the molecules. And the reason why it's such an incredibly high number or long time is because you have 10 to the 19 molecules. It's a huge number of molecules, okay? But now suppose that we have alpha equals 2. Again, I'd like to stress, I'm not looking at the mechanism right now. I'm not looking at the initiation, branching, and termination. I'm just looking at the branching step and trying to figure out why it can actually lead to a very, very fast reaction. So alpha equals 2. In this case, well, we can actually draw this. The situation is really different, right? Because now we have what? We have that the branching step actually produces 2 molecules of C, right? So we can have, at the second step, we can actually have 2 branching steps, right? 1 molecule of C reacting with R to produce P and another 2 molecules of C, but also this one can do it, okay? So you see now we have sort of, this is stage 1, this is stage 2, okay? Now, even here we have now a situation where we have given rise to 4 molecules of C. So you see what we're getting at here. Each of those will react with R. Etc. Okay, to produce P plus another 2C. Okay, I'll give you just, I'll just do this one here. So in fact, when alpha equals 2, well, we start from 1 so at this stage we start from the initial level, which is 1 molecule of C. Then we have 2 to the 1 molecules. Here we have 2 to the 2 molecules. Here we have 2 to the 3 molecules, because it's 8, 2, 2, 2, and 2, and so on, 2 to the 4th. So at every essentially collision process, we're actually in successive collisions, we're actually forming a geometric series, okay? So at level 1, we have 1 molecule C, then you have 2, then you have 2 to the 2, 2 to the 3, 2 to the 4, okay? And after n sort of successive collisions, you have, and from one to the other, you have essentially a proliferation of intermediate species, okay? And at the nth level, okay, you have 2 to the n. So in fact, you have a geometric series of the kind, well, generally speaking, you have the summation of some number r to the power of k, where k goes, for example, from A to B, okay? We have an analytical expression for the sum of this is r b to the b plus 1 minus ra, okay, to the a divided by r minus 1. Now, in our case, clearly r is 2. We start from 0, so a is 0, and we have b equals n, okay? So the summation will be, the final sum will be 2 to the n plus 1 minus 1 divided by 2 minus 1, okay? So what do we do with this? Well, remember, for each intermediate molecule, okay, we can react here. You can see it over here. For each intermediate molecule, we can react 1 molecule of R, okay? So essentially, to complete the reaction, okay, and transform all the reactant molecules R into final product, okay, because we had 10 to the 19 molecules of R initially, we need essentially 10 to the 19 collisions with C, okay? But clearly, now we have a lot more molecules of C. This is the number of molecules of C. So in fact, if you equate 2n plus 1 minus 1 divided by 2 minus 1, okay? And you equate it to 10 to the 19, which is the number of molecules that we have of R that we have to essentially get out of the system, okay, react with C, okay? What do we find? We find that N is equal to roughly 64. Very small number. What does that mean? It means that I have 64 steps here. This is one step, this is another step, this is another step, and so on, okay? And after 64 of those steps, okay, I will have produced 10 to the 19 molecules of C that can now react with R, and the reaction is completed, is depleted, okay? But remember, each step still has a frequency of 10 to the 8 collisions per second. So the time for these 64 collisions, okay, will be 64 collisions divided by 10 to the 8 collisions per second. This is what? This is roughly 10 to the minus 6 seconds. So 1 microsecond. So, long story short, okay? Now, clearly this is a paper and pencil, very, very fast estimate, okay? Well, first of all, you know, we have a huge difference between alpha equals 1. I'd like to remind you, we estimated alpha equals 1, okay, over here. We estimated a reaction time of, you know, tens of thousands of years. With only alpha equals 2, there you go, 1 microsecond, okay? Now, some of you may have seen a very, very close similarity with another phenomenon that's been going on in the past year, which is the spreading of the virus, okay? It's exactly the same, okay? It's exactly the same kind of process. It's actually a runaway process. It explains the fact why, I mean, the fact that the reason why, if you start from a very, very small number of infected people, which play the role of the intermediate species, if the virus is very infective, and clearly the infectiveness, okay, or how infective the virus is measured by alpha. So if, for example, for each infected person, you have 2 other infected persons, well, then very, very soon, okay? If you don't do anything like social distancing, okay, but if the frequency of collisions stays the same, okay, you are effectively having this runaway phenomenon, which is exactly the same thing that you have in combustion, okay? I said something about social distancing, okay? You see what's going on here. Effectively, by social distancing people, you're actually decreasing the collision rate, right? So the time for the process is now much, much larger, okay? And it will take a long, long time. And the fact that then, we haven't seen it here, but the fact that people then get out of the disease, so they heal, okay? will tell you that, again, there is no time for the virus to actually spread in an exponential way. So that's why we're social distancing. So we're acting on this denominator. In the case of combustion, clearly, what you can do is you can decrease the temperature. Then the collision rate will obviously decrease and the reaction time will increase. But what I'd like to underline is that the underlying process of alpha equals 2, okay, doesn't depend on temperature. It depends on the structure, the kinetic structure of the system. So if alpha is 2, the system, you can be sure, okay, will explode. Okay, and this is if clearly the collision rate is high enough. Okay? So this is what all of the combustion systems have in terms of their kinetic structure. Okay. Now, clearly, the situation is more complex, okay, than this. You'll see that if you look for any sort of virus models, okay, around, so in epidemiological models, they will be described by ordinary differential equations that are very, very similar, if not the same, as the ones we are going to be writing now. Okay. Now, why is it not as simple as this? Well, again, let me write down let me remind the overall system. So we have a reactant going to an intermediate, the intermediate reacting with the reactant to form a product and alpha intermediates, and then a termination step C, which closes the loop and depletes C to form the products. So we have an initiation step with a constant Ki. This is a constant Kb, and this is a constant Kt. So for this system, first of all, the first thing that we can do is we can write down a system of ordinary differential equations, right? So clearly, why is it more complicated? It's simply because you have this initiation step and this propagation step, and they will be essentially proceeding at different rates. Okay, so it's a little more complex. We now want to, let's say, examine the situation a little bit closer, because we will realize that there is, in fact, this fast-slow dichotomy, or this fast-slow behavior that we've seen all the time, okay, in combustion processes. So let's write down the equations. Let me just use this notation, okay? CR is simply, what I mean by CR is the molar concentration of R, okay? So C is just the molar concentration of C, and so on, okay? So clearly for R, the rate of change of molar concentration, for the dimensional time, we'll use tau this time. Okay? Well, look at the first reaction. This will be minus Ki CR, okay, for this reaction here. And for the second reaction, we have minus, clearly, Kb's, because clearly the minus signs indicate that it's being depleted, and then the product of the molar concentration of C and of R, right? This is the second reaction here. What about the intermediate? The intermediate, so we have the rate of change of molar concentration of C. Well, the first reaction will have a plus sign, because clearly C is being produced in the initiation step. So again, it's KICR. Now the second step, you have to look at the difference between the stoichiometric coefficient. So it's alpha here in the product side -1. So it's alpha -1, okay, for C, and then clearly the products of concentration of that you have on the left side, which is CC CR. Clearly, I forgot to multiply by KB. And then here we also have the termination step, which depletes the intermediate C. It's simply minus KT CC. The only thing we have to look at here is that, well, always look at the units, okay? Clearly, this is a molar concentration per unit time, okay? So because you have a molar concentration here, you see that the units of Ki, it's unimolecular, so it's 1 over time, okay? On the other hand, because you have here essentially a molar concentration squared, essentially, KB has different units. It has units essentially of 1 over molar concentration times time. The 1 over molar concentration and 1 over time. Okay? Another thing that is interesting is the fact that, well, look at P. These are all irreversible reactions. P is always on the right side, is always on the product side, so it does never appear in this system, okay? So it's really irrelevant. So in fact, this system is a two-dimensional system, okay? Between, let's say, the reactant and the intermediate, okay? So it's irrelevant. It doesn't take part in the determination of the two functions of time, CRT and CCT, right? So you may have now understood the fact that what I want to do now is try to see if I can use some of the techniques that we have learned. For example, the singular perturbation technique, okay, or theory, and see if I can cast this system of two ordinary differential equations into singularly perturbed form. So I have to essentially, again, I'll remind you, right? So come up with, well, non-dimensionalize the system in a sort of in a rational sort of way, and also extract a small parameter epsilon, which is representative of the fast to slow time scales. Now, what do we mean by fast and slow time scales here? Well, usually in combustion, we can safely say that the initiation step, this one, okay, is a slow reaction, okay, or at least it's slower, okay. So it's let's write it slower, okay, than the branching step, which is faster, okay. So again, what this means in some sense is that Ki is smaller than Kb, but the fact of the matter is that we can't really say that because there are different units, okay? I just told you that Ki and Kb are different units, so I can't really say Ki as much smaller than Kb. So I'll write it here, but then I'll just erase it. Okay, we need to do something a little bit more sort of elaborate. There's going to be a molar concentration somewhere. So let's see. So first of all, what I can do is, well, for sure, I can say that the tau I, which is the time scale of the initiation step, okay, is 1 over K1, because K1 has units of 1 over time, okay? So for sure, we can say that, I'll just repeat it here, K1, okay, has the units of 1 over time, okay? So this is the slow time scale of the initiation step. This is tau I. You can still hear me, right?
Sì, sì.
Yeah, professor.
Yes, professor.
So what about the fast, okay, a time scale associated with the branching step? So let's call it tau B, the time scale of the branching step. Well, what we can do is very simply define it in this particular way. So it's 1 over Kb, but then we're left with, you see, units of time times a concentration. So we can divide by a concentration, C, and the only concentration that makes sense to use here is the initial concentration of the reactant. Okay, clearly the initial concentration of the intermediate species may be 0, so we would divide by 0. So we're simply dividing by the initial concentration of R. Okay? So you see that with respect to what we did at the beginning of the lesson, now we're getting into not only, well, into the inner working of this mechanism. Not only do we have a chain branching mechanism, but we also have two processes that are fast and slow, okay? So it's a little bit more complicated. Okay? Well, we introduce, therefore, if we define two time scales, one is slow and one is fast, what we can now do is we can introduce a small parameter epsilon, which is essentially the ratio of tau B over tau initiation, the tau branching over the tau I. Again, this is the fast time, so it would be a small number. This is a slow time. So this will be hopefully less, much less than 1. Being clearly the branching time scale much smaller than the initiation step. So epsilon is given by Ki over Kb CR0. Okay? So we've introduced this number epsilon. Now we have to choose a proper set of non-dimensional variables representing the concentrations. Okay? So what concentrations do we have? Remember, we have CR and CC, right? Concentration of the reactant, concentration of the chain carrier. We need to non-dimensionalize this, okay? That's what we're doing. We are non-dimensionalizing our system of ordinary differential equations. So we can introduce, for example, the non-dimensional concentration for R, and we call it X, okay, as CR divided by CR0, okay? Now, and this makes total sense, right? Because we start with an initial concentration of R, so we non-dimensionalize with the initial concentration. What about the intermediate we call the non-dimensional variable for the intermediate concentration. Why? So this would be the concentration of C divided by, well, divided by what? Divided by some representative concentration, okay? Now, we cannot clearly non-dimensionalize with respect to the initial concentration of C, okay? Because that would be 0. What we can do, however, in order to find sort of a representative concentration is remember that the ratio Ki on Kb, okay, actually has the units of a concentration. Okay, and we're talking about the ratio of the rate constant of the initiation step to the rate constant of the branching step. So that's a reasonable choice that we can do. So we can divide by the ratio of these two, which is a concentration. Okay, it's a number, it's a constant. Okay, there is no easy sort of or unique way of proceeding here. Okay, and again, what we have here, because Ki and Kb, okay, are a function of epsilon, we just wrote it here. So what we're doing here is actually non-dimensionalizing by r, but we're also dividing by epsilon, okay? So this makes sense because we're introducing essentially also epsilon in our non-dimensionalization. And then what we do is we go back to our system over here and we substitute our variables, okay? I haven't talked about time yet. Time is still dimensional. We'll do it later. So let me just write down what we get. So for example, the first one, we substitute for CR, we substitute X times CR0, and so on. So this is pretty straightforward. So minus Ki CR0 X minus, again, Kb, and then we have to substitute we have to substitute Ki times Kby, here it is, Ki times Kby instead of Cc, okay? So you see that we have Kb and Kb that goes, CR0 cancels throughout, okay? The same thing here, so we substitute for y, so Ki over Kb dy by d tau is equal to Ki CR0 x. Then we have alpha minus 1 Kb, then Ki over Kby, substituting for Cc, and then Cr is simply CR0x, right? And the last step is Kt, Ki over Kby, okay? So, Well, okay, let me take it. I'll give you enough time to write it. So let me just write an intermediate step here. So dx by d tau is equal to minus ki x minus ki yx, okay? And dy by d tau, okay? Remembering that ki, there is this relationship here, okay? We have epsilon here, because essentially we have CR0 again that cancels. Okay, so we have KIX. Okay, this, once you do it, I mean, by yourselves, it's really straightforward. YX, and then we have essentially divided by CR0, so we have KT over CR0, and then again KI over KB and Y. So we haven't finished yet, because clearly a fully non-dimensional system is a system where you have no dimensional variable appearing. Okay, well, we still have the time that is here, that is dimensional. So we need to introduce a non-dimensional time, which we can very easily define as tau, okay, times a representative quantity with the units of 1 over time, which obviously is ki, okay? Because clearly ki has dimensions 1 over seconds, so times seconds is a non-dimensional variable, okay? If we substitute this, we finally get something of this sort. So now I'm using t, okay? And as you can see now, this ki disappears, which we're happy about. So it's minus xy, okay? And then here, dy by dt is 1 over epsilon, okay? X plus alpha minus 1, xy minus, I'll define a new variable gamma, y, where gamma is this group here is essentially kt divided by kbcr0. So it's in some sense has the same significance of epsilon, but referred to the termination step. Okay, but for the sake of this analysis, gamma, we can consider it as a constant. Okay, we can consider this a constant. For example, gamma equals 2. Okay, and leave it fixed. Okay. What we are going to look at, well, clearly is epsilon, and alpha is our only, let's say, important surviving parameter. Alpha has a very important physical meaning. Again, it's the branching constant, okay? But you can see that this final system is in a singularly perturbed form. Why? Essentially because, you see, dy by dt is of the order of 1 over a very small number. So dy by dt, the rate of change of the variable y, which I remind you is associated with the non-dimensional concentration of the intermediate, is a very high number. It's a very, very large number, meaning that the intermediate is the fast species. So this is the fast ordinary differential equation. This is clearly the slow one. in the sense that x will evolve on a time scale of order 1, whereas y will evolve on a time scale of order epsilon, okay? But again, what's nice is that we were able now to cast the system in a singularly perturbed form. So now, why is it important? Well, first of all, let me just say that the point, the origin, so xy equals 0, 0, is an equilibrium point. Can you see that? If you substitute 0, 0 for x and y, you have that the two time derivatives are 0. So it's clearly a stationary point. So dx by dt is equal to 0, dy by dt is equal to 0. So clearly x and y are constant and equal to 0, clearly. So the origin is an equilibrium point. Good. So clearly what that means is that there is no reactant, so x equals 0, there is no intermediate c equals 0, and there is only product, clearly. So we have completely brought the process to the end. Okay, these are all irreversible reactions, so eventually they'll all get to a point where you only have product. Okay. So again, we said that gamma is constant. So what do we do usually with singularly perturbed systems? Well, in order to find the asymptotic behavior, what we do is we let epsilon go to 0. Okay. This represents the asymptotic behavior of the system. Why? Essentially, we have two processes, one which happens on a time scale of order epsilon, the other on a time scale of order 1. So what we do is we shrink to 0, okay, the time scale, the very fast time scale. So what we're doing is we're only looking at, again, not the boundary layer, which is shrunk to 0, but the outer solution, okay? So what do we have? Well, if we let epsilon equal to 0, we have a surviving ordinary differential equation, minus x minus xy, which represents the asymptotic slow evolution. And then the fast evolution is really reduced to an algebraic constraint. Which is this, okay? In fact, if you've been paying attention, we have two groups here of terms. If you see. One group, well, if alpha, for example, is bigger than 1, can be called omega dot plus, and this omega dot minus. You remember when we did the quasi-steady state assumption? Now I'm mixing the two techniques together, okay? Because sometimes they can be equivalent, okay? Now, by placing epsilon to 0 in the singularly perturbed form, what we're actually doing is something very similar to the quasi-steady state assumption, because if we consider y as being the fast species, okay, what we've done is we've said, okay, we have neglected dy by dt, okay? So after the the initial transient, where essentially omega plus and omega minus are big numbers, okay? But they sort of balance out, remember? Now, we're not doing this in singularly perturbed approach, we're only putting epsilon to 0. So we're doing something completely different. But morally, they're equivalent because both are saying, okay, let me let me consider the initial transient as being very, very fast, so that the rate of change of y outside of that transient becomes very, very slow, okay? Very, very small. So dy by dt. Now, in the case of the quasi-steady state, we're saying it because these two terms balance out. In the case of the singularly perturbed theory, we're saying it because epsilon goes to 0. So it's this parameter here that we put on this other side. At the end of the day, what do we have? We have an asymptotic behavior, okay? And this guy here, the sort of algebraic constraint, remember, was what we called M0, what we called the reduced slow manifold, okay? In fact, M0 was the set of points, in this case x and y, such that we could actually take the fast variable and express it as a function h0 of the slow variable. Okay, so we're not integrating for this variable an ordered differential equation, but we're actually having a constraint. We're having an algebraic constraint. And can we solve for y? Yeah, I mean, it's very simple. Look at this expression here. We just solve for y, and we have that, I'll write it here. Y is equal to h0 of x, which is this function here. X divided by gamma minus alpha minus 1 x. Okay, so it's a graph, it's a function, a very easy function of the plane y and x. Okay. We can do some high school kind of analysis of this function here. You can see that this is x and this is y, right? You can see that x equals gamma divided by alpha minus 1 is an asymptote, right? Is a vertical asymptote when y goes to infinity, okay? So you see that, well, gamma, we said that it's a constant, okay? It doesn't really matter what it is, so let's say 2. You see that now the vertical asymptote depends on whether alpha is bigger or smaller than 1. So suppose that, for example, alpha is smaller than 1, okay? Then you see that this vertical asymptote is actually on the negative side here. Now, does that make any sense to be on the negative side? No. But that doesn't stop us from graphing this everywhere, okay? Then clearly, the only region where it makes sense for us to see things is on the positive quadrant here, because these represent species. So clearly, you don't have negative concentration. So you have here the reactant, and this is the intermediate. Actually, there is also another asymptote, which is horizontal. So we just solve for, instead of for y, we just solve for x. Okay. And if you solve for x, you should get something like gamma y divided by alpha minus 1, y plus 1. Okay? So we should have also this asymptote here, minus 1 over alpha minus 1. Okay? So you see that there's a minus sign. So if alpha is smaller than 1, this is a positive value. Okay? So this would be minus 1 over alpha minus 1. And this is gamma over alpha minus 1. Okay? So let's try and graph this M0, and we have something like this. Okay, something like this. So it goes through the origin, because clearly this is a physical equilibrium point. And so what this is saying, this graph, this M0 here, we can write down here, this is M0, it's actually representative, so I'll just put an arrow here, of the slow dynamics. Okay, in fact, the slow dynamics is represented by, on this manifold, by this equation here. Okay, so we solve essentially this system, this ordinary differential equation, with this algebraic constraint. Okay, and we're traveling, okay, on this manifold here, okay, with this sort of slow dynamics given by this. Now, of course, this is only valid for, again, M0, so for epsilon identically equal to 0, so essentially epsilon tending to 0. Okay, clearly you can have a situation where epsilon is small, but it's not, again, it's not 0. Okay. The reason why, let me just go down to the quasi-steady state, okay, and the quasi-steady state leading to the same result. So if we go back to, well, I can write it here. If you decide that C is your fast intermediate species, okay, and you rewrite dc by d tau equals, well, I don't want to write it again. Well, I'll write it again for completeness. So this is the very first thing that I did before. We have non-dimensionalized. Okay, and essentially you now have well, alpha is less than 1, so you have essentially, this is omega minus and this is omega plus. Okay, so you consider this as being approximately 0, and then you non-dimensionalize, you get exactly, okay, this process here. So you're actually having a constraint between two variables. So you don't have to solve two ordinary differential equations, you only have to solve one, and the other one is simply the fast variable as a function of the slow variable. So once you know the slow variable from this, okay, obviously you would have to substitute for this y here, you would have to substitute clearly this expression here, okay? So, this is, well, we found the slow manifold. Again, okay, we have 15 minutes, so I have to keep up the pace. It's not that we have learned anything special here, right? Well, let me complete. We will in a second. That's what I'm saying. We will at least have a geometric explanation of what's going on in 1 second. So we have the slow dynamics. What about the fast dynamics? Remember the fast fibers? Okay. So if you remember, epsilon going to 0 means that we're shrinking to 0 the time scale of the boundary layer, of the initial transient. What if we rescale the system, or better, the time? We have a fast time, which is t, the non-dimensional time that we had before, divided by epsilon. Now, essentially, you will have that what was slow before will be extremely slow, okay? And what was fast below becomes essentially order 1, okay? So we are dilating the boundary layer, okay? So what you get is something like this, dx by dtf is equal to epsilon, okay, minus x minus xy, okay, and dy by dtf, okay, is equal to x plus alpha minus 1 xy minus gamma y. Okay, so this is what is called the same system on a fast time. Okay, so by playing with these time variables, we're actually dilating time so that we can actually highlight, in the first case, in the previous case, the asymptotic behavior. In this other case, we're really highlighting what's going on in the first transient, okay, by dilating. So essentially, the slow dynamics is so slow, okay, and if I put epsilon going to 0 in this case, you essentially have that the first equation will tell you this, okay? The slow variable is so slow that in fact doesn't change. So in fact, x equals constant. Okay, so what we're doing here is defining these fast fibers as the locus of points such that xy x equals constant. So what we're doing is defining for all y, by the way, so we're defining a set of vertical lines, and that is our fast, like this, okay? And these are our fast fibers, okay? And I'm adding an arrow here because we know that M0 is attractive for all trajectories because it's the asymptotic dynamics, okay? Let me write this here. Asymptotic dynamic, this is the fast transient. So on this plane, we now have a complete backbone of the dynamics, okay? We start, for example, here. This, remember, the x-axis is the reactant, okay? And this is C, the intermediate. So you see what's going on here. We start from here. There's no intermediate, so y equals 0, for example. We go all the way up. This is for epsilon equal to 0, okay? And then, so we have this initial production of intermediate species, and then a very, very slow or slower, which is, by the way, very fast. So there's a very fast production of intermediate species, and then a sort of slow process whereby both the intermediate species and the reactant, they all produce, or they all react to produce the product, okay? And at the end, there is no reactant and no intermediate left. There will be only product. We can't see the product here, okay? It will be on the third axis, but it's really relevant, okay? So by looking at this, it's really starting to emerge, and we haven't integrated anything numerically, by the way, to emerge a picture that the way these chain branching systems work is that the initial transient will produce, well, sometimes it's called a pool of radicals, okay? And then on a slower asymptotic time scale, this pool of radical will react with the reactant and will deplete this pool and both the reactant to produce the product. Okay, so this is the sort of the what's going on with the dynamics of this system. Okay, but there's a problem. How large is this pool of radicals? Okay. Well, in this case, remember alpha is less than 1, okay? So we have these two asymptotes here, this and this, especially this one here, look, will sort of limit, in some sense, the growth of this radical pool, okay? And remember that the possibility of having a radical pool very fast really will eventually contribute to the explosion, okay, or the explosive nature of the combustion reaction or chain branching reaction, okay. So this initial sort of, let me just write down the fast transient of order epsilon. This is of order 1, the time scale of evolution, okay? So from this figure, what you can see is that the initial, in the initial transient or of order epsilon, x, essentially the reactant remains virtually constant, okay? While y, which is the pool, as I said, the radical species will increase, okay? But this increase is bounded, okay? There is a limit to which this can increase simply because, look at this, eventually you're going to get to the manifold, M0, okay? And so, essentially, you'll very soon, after order epsilon, very soon, you will essentially be dominated by the controlling aspect of this, which will be, for example, the slow initiation step. So there is no formation of the radical pool, okay? Now let me show you what happens when alpha is bigger than 1. If alpha is larger than 1, you essentially have that, okay, let me just write it over here. You essentially have that now the vertical asymptote is somewhere here, okay, on the positive quadrant. And the horizontal asymptote is here. So the shape of now your asymptotic behavior, your slow manifold, is something like this. Okay, this is M0. So you see how we're actually before it was different, right? Before it was, remember, something like this. This was M0 for alpha less than 1, okay? So this is a totally radically different shape, right? In the sense that, and this is for alpha bigger than 1, okay? now, essentially, in the order epsilon transient, the radical y is not bounded anymore, you see? And it can create a huge pool of radicals, okay? Like this. And eventually, it will lead to your slow evolution, okay? Where this pool is essentially slowly then producing the oxidizing components or the products of the oxidation, the product P, going finally to zero. So we found out that alpha, okay, is a sort of a bifurcation parameter, okay? And really, if alpha is less than 1, you really don't have any role being played by the intermediate species, okay? Essentially, what you have is a reactant giving to a product in a very slow manner, okay? And the intermediate species doesn't play any role. On the other hand, if alpha is bigger than 1, you essentially have this huge production of radical pools, okay? Which contributes, by the way, eventually to also the depletion of the reactant very fast, okay? And then you'll have essentially still a slower process going to the product. Now, if you associate this essentially to the final step, also to the production of heat, you soon find out that really the production of the huge sort of radical pool, I'll just place it here. You associate this to an explosion and obviously to a very, very large output of heat, okay? So if you output heat, of course, you have thermal expansion and so on. So this is what you're used to, okay, seeing, okay? Then obviously we're going to see that there's going to be a flame associated with it and whatnot. But in an homogeneous, okay, reaction, spatially homogeneous reaction, clearly, this means that it happens all in every single point, okay? So there is a huge expansion. Clearly, if there is no radical pool, then you have a very slow process, okay? Where you have much less, okay, production of, for example, of recombination and therefore of heat. But clearly, this is what happens all the time in combustion. Clearly, the production of intermediate pools of radicals of intermediate species of many kinds. So C is just representative of one. C is essentially representative of many, intermediates, which are very reactive, okay? Now, if you were to take a computer and integrate this numerically with MATLAB, for example, let me just write down, this is M0. Let me just remind you, M0 is only valid when epsilon is 0, okay? So this is just an approximation. If you are to integrate the actual system, okay, the slow system, not the fast system, so this system here, this one here, okay, you would get something that reminds us, okay, of this sort of behavior, and it would be something like this, for example. Okay, this is the actual system. You see that there is a crossing. This is going to be very close, but it's not going to be on it because this clearly M0 is not invariant. Okay. And this is obviously for alpha equals to 0, so you have this sort of large explosion. On the other hand, for this kind of system here, you will have a very, very small kind of radical pool like this. Okay. Think of it in terms of virus. Clearly, the bifurcation problem clearly will tell you whether the virus will spread or not. Okay. Clearly. Now, there is also a last step that we don't have time today to do, which is, well, how do I find m epsilon, which is essentially representative of this function here, okay, where essentially h epsilon is a series, okay, expansion of, remember, so it's a consecutive series expansion in terms of epsilon of higher and higher order terms. This is what we found, okay, M0, okay? This would be an M1 correction, this would be an M2 correction, and eventually this is invariant. So we find the actual right slow invariant manifold, okay? We're not going to do this. Maybe we can sort of do it tomorrow at the beginning of the lesson. But I told you how to do it last time, okay? So you just substitute, sort of iterative substitution, okay? So, okay, we're out of time. Let me put one sign here. And so this is how we approach the analysis of the chain branching system, okay? Essentially, we have determined whether for alpha less than 1, we cannot have this formation of a radical pool, and for alpha bigger than 1, we have a sort of an unconstrained, okay, explosion with the formation of this radical pool of intermediate species, okay? And we saw this geometrically and analytically with the shape of M0 and having asymptotes. Clearly, the other asymptote, no, okay, I found it, okay? Good. I hope you can hear me still.
Sì, si sente.
So let me stop recording.